Welcome to another module in this massive open online course on the principles of CDMA, MIMO, OFDM wireless communication systems. So, in the previous module we have seen the SVD, the singular value decomposition, and we have said that the singular value decomposition can be used to gain insights and analyze the properties of MIMO wireless communication. Let us now look at the applications of the SVD, that is the singular value decomposition in MIMO wireless communication systems. So, what we are going to look at today is the application of SVD, that is singular value decomposition in MIMO transmission. Or in MIMO systems basically. And SVD, as we have already mentioned, stands for singular value SVD stands for singular value decomposition, and SVD can be employed for MIMO communication. It can be employed as a tool, as a valuable tool for MIMO wireless So, SVD can be employed as a valuable tool for MIMO wireless communication. Let us look at an example, let us look at how the SVD is employed in MIMO wireless system. So, we have the channel matrix H, this is the MIMO channel matrix. And we said that the MIMO channel matrix can be decomposed using the singular value decomposition as the product of three matrices U sigma V Hermitian, where we have the following properties: U Hermitian U equals identity, also V Hermitian V Hermitian V equals V Hermitian equals identity matrix, and sigma is a diagonal matrix of singular value. Sigma is a diagonal matrix of non-negative singular values. Sigma is a diagonal matrix of non-negative singular values. So, what we are saying is that the channel matrix H can be decomposed as U sigma V Hermitian, where the matrices U and V satisfy the property that U Hermitian U is identity, V Hermitian V is identity, and sigma is a diagonal matrix containing the non-negative singular values sigma 1, sigma 2 up to sigma t. In fact, these non-negative singular values are arranged in the decreasing order or descending order. That is what we said is a singular value decomposition. Now, let us go back to our MIMO system model. Let us go back to our MIMO system model. So, consider the MIMO model. Consider the MIMO communication model. We have y bar equals h x bar plus w bar. This is our MIMO communication system model with y bar. This is our r cross 1 receive vector. This is the r cross 1 receive vector. This h is the r cross t channel matrix, x is the t cross 1 transmit vector, and w is basically your r cross 1 noise vector, correct. So, these are the different components. Now, we employ the SVD. Now, for H, in this equation for H, substitute the SVD, that is H equals U sigma V Hermitian. So, in this equation, in this MIMO system model, what we are going to do is we are going to replace H by its singular value decomposition, that is H equals U sigma V Hermitian. So, now substituting, what I am going to have is I have y bar equals, I had y bar equals H x bar plus W bar. Now, substitute for H by its SVD. So, I have y bar equals U sigma V Hermitian times x bar plus W bar. Now, we employ receive processing. At the receiver, we perform multiply by U Hermitian, that is what we are going to have is U Hermitian y bar equals U Hermitian U sigma V Hermitian x bar plus W bar. So, at the receiver we are employing post processing, that we are multiplying the receive vector y bar by U Hermitian, by the matrix U Hermitian, and therefore, what we get is basically we get, let me call this U Hermitian y bar as y tilde, we get y tilde equals U Hermitian U sigma V Hermitian x bar plus U Hermitian W bar. Let me call this U Hermitian W bar as W tilde. Now, you see I have U Hermitian U is identity, therefore, this reduces to y tilde equals sigma V Hermitian x bar plus W tilde. So, what we are saying is that once you multiply at the receiver by this matrix U Hermitian, I have U Hermitian y bar, we are denoting by y tilde, I have y tilde equals U Hermitian U times sigma times V Hermitian x bar, but U Hermitian U is identity, as a result I have y tilde equals sigma V Hermitian x bar plus W tilde, where W tilde is U Hermitian times W bar. So, this is the net system model I have at the receiver, that is y bar equals sigma V Hermitian x bar plus V Hermitian x bar plus W. In fact, I have y tilde, this is y tilde equals sigma V Hermitian x bar plus W tilde. Now, what I am going to do at the transmitter, we perform x bar, that is the transmit vector x bar is equal to V, transmit vector x bar is equal to V times x tilde, and this is termed as precoding. This is termed as precoding. What we are doing is we are pre-processing the transmit vector, that is we are transmitting x bar, where x bar is equal to V, the matrix V times x tilde, where x tilde is the vector that contains the transmit symbols. So, we are pre-processing the transmit symbol vector, that is pre-processing x tilde by multiplying by the matrix V. So, we have x bar equals matrix V times x tilde. Now, let us substitute this expression of x bar in the above equation, and therefore, what we obtain is we obtain y tilde is equal to sigma, y tilde is equal to sigma V Hermitian x bar, but x bar is V times x tilde plus W tilde. And now, you can see what we have is V Hermitian V is identity, therefore, this reduces to y tilde equals sigma times x tilde plus W tilde, and this is something very interesting. Let me rewrite this again over here. I have y tilde equals sigma times x tilde plus W, y tilde equals sigma times x tilde plus W tilde, where y tilde is a t cross 1 vector, sigma is a t cross t diagonal matrix, x tilde is a t cross 1 symbol vector, W tilde is a t cross 1 noise vector, and therefore, now if you look at this system, I can write y1 tilde, y2 tilde, so on, yt tilde equals this diagonal matrix sigma, that is sigma 1, sigma 2, sigma t, which is a diagonal matrix times x1 tilde, x2 tilde, xt tilde plus w tilde, which is w1 tilde, w2 tilde, wt tilde. And therefore, what you have is you have the net result is that you have this matrix y tilde is equal to, well, the diagonal matrix sigma times the symbol vector x tilde plus the noise vector w tilde. And now, if you look at this, because sigma is a diagonal matrix, you have a very interesting structure. What you have is basically you have y1 tilde equals sigma 1 x1 tilde plus w1 tilde, y2 tilde equals sigma 2 x2 2 tilde plus w2 tilde, so on. You have yt tilde equals sigma t xt tilde plus wt tilde. And if you look at this, this is a combination of t parallel channels. What is this? This is t parallel wireless. So, what you are observing is that because sigma is a diagonal matrix, you have y1 tilde equals sigma 1 x1 tilde plus w1 tilde, y2 tilde equals sigma 2 x2 tilde plus w2 tilde, so on and so forth. Yt tilde equals sigma t xt tilde plus wt tilde. So, what you have is you have a combination of t parallel wireless channels. So, between the transmitter and the receiver, you have t parallel channels where you are transmitting x1 tilde, x2 tilde, xt tilde, and correspondingly you are receiving y1 tilde, y2 tilde, yt tilde. That is basically on the ith channel you are transmitting xi tilde and you are receiving yi tilde, and therefore, you have t such channels or you have t parallel channels, therefore, you are able to transmit t parallel data streams or t data streams in parallel. This is termed as spatial multiplexing. This is precisely what is termed as, So, what you have as net is basically for I is equal to, that is on each channel, that is you have yi equals sigma I xi tilde, yi tilde equals sigma I xi tilde plus wi tilde, where yi is received symbol on ith channel, sigma I is the gain of ith channel, x tilde I is transmitted symbol or transmit symbol for ith channel, and w tilde I is noise for noise on ith channel, which is Gaussian. This noise w tilde I is Gaussian with variance sigma square. So, what we have as a result is we have T decoupled channels. We also have, we can also call this as decoupled channels, because these different channels, you can see these have these decoupled inputs x1 tilde, x2 tilde, xt tilde, and the decoupled outputs, that is y1 tilde, y2 tilde, yt tilde. So, you have these T parallel channels between the transmitter and receiver. So, you are able to transmit T streams of information or T symbols across these parallel channels between the transmitter and receiver. This principle in a MIMO system is precisely what is termed as spatial multiplexing. So, there are T parallel channels. So, for I equals 1, 2 up to T, there are T parallel channels which implies that T streams of information, which implies T information symbols can be transmitted in parallel, and this is what is termed as spatial. This is what is termed as spatial multiplexing. As we discussed in one of the first modules on MIMO, spatial multiplexing means multiplexing multiple streams of information using the space dimension. So, what are the multiple streams of information? The multiple streams of the information are the multiple symbols x1 tilde, x2 tilde, xt tilde. We are multiplexing these symbols over the same frequency band at the same time by exploiting the space dimension in this multiple input, multiple output wireless communication system. This is termed as spatial multiplexing, and therefore, what we have seen is basically we have seen how the SVD or the singular value decomposition now helps us basically decouple this MIMO wireless communication system into T parallel channels for the transmission of T independent information symbols, and this phenomenon is termed as spatial multiplexing. Therefore, what we have seen is basically this is termed as spatial multiplexing, and basically this is how the SVD, basically what we have seen is how the SVD can be employed for spatial multiplexing. So, with this we will conclude this module over here, and we will continue with other modules on MIMO in the subsequent lectures. Thank you.